Hi, this is Naresh Kumar Gurulingan. I am pleased to present a work on UniNet, a unified scene understanding network, and exploring multitask relationships through the lens of adversarial attacks. This is a joint work with Alaya Arani and Bahram Zunos. A large number of recent advances have been made in single tasks, such as object detection. We aimed at incorporating these advances into a unified scene understanding model. UniNet predicts five different tasks, namely object detection, semantic segmentation, instance segmentation, depth estimation, and instance depth prediction. UniNet provides an acceptable trade-off between accuracy and inference efficiency while retaining a simple architecture. UniNet can also be used as a good framework to study multitask relationships, based on which we can leverage complementary information sharing. We also use adversarial attacks as they likely reveal vulnerabilities resultant of learned task relationships. Related works can be categorized into three broad groups. The first group of works address multitask architectures. State-of-the-art architectures include MTAN, cross-stitch, PadNet, MTI-Net, and others. While these architectures have their own elements, UniNet provides a simple asymmetric encoder-decoder architecture. UniNet also includes an FPN branch to predict instance tasks. The second group of works revolve around understanding task relationships. Stanley et al. Empirically study multitask relationships. Task transfer relationships have also been studied using empirical approach, representation similarity analysis, and attribution maps. The third group of works concern adversarial attacks. Adversarial attacks have been used against single task networks. Multitask networks have been shown to improve robustness. Unlike prior works, we use adversarial attacks as a tool to study task relationships. Here we present the UniNet architecture. The encoder consists of 6 stages, while the decoder consists of 5 stages, resulting in an asymmetric encoder-decoder. The instance head contains FCOS object detection, instance segmentation, and depth per instance prediction. The segmentation head and the depth head have a similar architecture. UniNet is accurate, fast, energy efficient, and provides a framework to study multitask relationships. We compare UniNet with state-of-the-art models in two datasets, Cityscapes and NYU-V2, using different metrics. All models are trained on semantic segmentation and depth estimation. The models are divided into three row-wise groups: baselines, slow models, and real-time models. UniNet is the fastest and most energy-efficient model. MTI-Net has the best performance across all models. In the real-time models group, UniNet has the best performance. UniNet therefore provides the best trade-off between performance and inference efficiency. UniNet achieves good performance across all tasks in the 5-task combination. Here we also include the results of using single tasks in UniNet and a few 2-task combinations. All task combinations are evaluated and the results are available in the supplementary material of the paper. We use UniNet trained with 5 tasks to perform all the adversarial attack-based task relationship analysis. PGD attack is performed by using 3 different losses as the attack objective: multitask loss, semantic loss, and geometric loss. Multitask loss is the combination of all task classes. Semantic loss is the sum of object detection regression loss, object detection classification loss, segmentation loss, and instance segmentation loss. Geometric loss is the sum of depth loss and the instance depth prediction loss. We observe that the multitask loss affects all tasks. The 3 semantic tasks in the green shaded region are affected more by the semantic loss based attack in comparison to the geometric loss. The same holds true for geometric tasks. Next, we use the semantic category hiding attack. The attack aims at hiding specific objects from predictions. First, we see hiding persons from segmentation predictions. From the segmentation prediction, a mask containing persons is taken. The person regions are then filled with the class of the closest non-person pixels, which gives the target segmentation. Using this target and the segmentation laws, the attack generates an adversarial image. Hiding from depth predictions is also similar. The mask and the region to fill is again obtained using segmentation predictions. The depth predictions in this region are filled with depth values from the nearest unmasked region. Using this target and depth laws, adversarial images are generated. The predictions for a particular image and its corresponding adversarial images is shown in this visualization. The first column is the input image. The second column visualizes the object detection and instant segmentation predictions. The third and the fourth column visualize the segmentation and depth predictions. In the second row, we see that persons are hidden from all predictions and the attack targets segmentation predictions. The third row, when the attack targets depth predictions, even though persons fade into the background in the depth predictions, persons still remain in segmentation and instance predictions. However, the shape of the persons in the semantic predictions are affected. When segmentation attack is used, all tasks are fooled likely because all levels of representation are disrupted. Under depth attack, semantic tasks still retain some predictions, but the person shapes are affected, likely because the lower level representations are disrupted. We infer that geometric attacks mainly disrupt low level representations, as abstract information might not be relevant for these tasks. In low level representations, both kinds of attacks are effective, and tasks slightly interact strongly. As we move towards higher layers, the interaction becomes weaker, as semantic tasks are still able to classify persons based on high level representations. We also perform quantitative evaluations. Under the corresponding task attack, only around 14% performance is retained. Under depth attack, segmentation retains 63% performance, while under segmentation attack, depth only retains 55% of its performance. Segmentation attack is slightly stronger as it affects all levels of representation. In this attack, we focus on classification branch of object detection. The attack is called tag attack. Out of all predictions, car predictions is changed to person and person predictions is changed to car. This target is used to calculate classification loss, which is then used as the attack objective. The attack is successful if it swaps car and person predictions. The plots show the MAP classification loss and the regression loss of person and car class before and after attack. The MAP of both classes drops after attack. Both losses increase for both classes. Therefore, the attack is successful in fooling the model by switching the classes. The person and car classes were picked as in general their orientations are perpendicular to each other. Persons are vertical and have an aspect ratio of less than 1. Cars are horizontal and have an aspect ratio of greater than 1. The green shaded region represents vertical boxes and the red shaded region represents horizontal boxes. In both clean and tag, the top bar represents person and the bottom bar represents car. Before and after attack, person boxes retain their mean aspect ratio. Same holds true for car class. Retention of aspect ratio is only possible if the regression branch also switches the orientation of the predicted boxes, as the classification has already been switched. This reveals that object detection has learned a bias towards shape as a resultant of the inter-task relationship between its branches. The visualization depicts this bias where car predictions on persons still retain their horizontal orientation. We perform ablation study by adding the UniNet instance head to MTI-Net. We call this network MTI-Net++. PGD attack reveals similar results. The tasks are affected more by the corresponding kind of loss. Under tag attack, object detection branch has learnt a shape bias. This is evident in these visualizations where the car prediction on persons are still horizontal. Under segmentation category hiding attack, geometric tasks are fooled just by disrupting low-level representations, while semantic tasks are only fooled after disruption of all levels of representation. The same inference that the interaction between semantic and geometric tasks becomes weaker as you move towards high-level representation holds. Segmentation retains 64% of its performance under depth attack, while depth only retains 41% performance under segmentation attack. All the inferences made are the same as the ones made with UniNet. Therefore, the inferences are architecture agnostic. Here we summarize this work. We first presented UniNet, which is a simple, performant, and inference-efficient multitask network which infers 5 tasks. We introduced adversarial attacks to obtain insights about multitask relationships. We observed that semantic tasks affect geometric tasks more than geometric tasks affect semantic tasks. We saw that the interaction between semantic and geometric tasks become weaker as we move towards high-level representations. Finally, we saw that the inter-task relationship between classification and regression branches in object detection induces a desirable shape bias. Thank you for this opportunity.